Thanks, Liz. So good morning, everyone, again. Welcome to the morning session. And we start off with something already very exciting. The first speaker of the day, Faherty, American Museum of National History. We will hear about directly imaged exoplanets in the year of Gaia.
Okay, is this on or no? Was it on? I didn't actually try and push it. Okay, good now? Yes, and people on Zoom. So good morning, good morning, good morning. Day 4, Thursday. Thank you guys for arriving close to on time, 8:30. Directly imaged exoplanets in the era of Gaia. We finally arrived at the topic you've all been waiting for. To see what these things look like and to learn how Gaia is helping us disentangle all the complications of understanding this data that's coming in from the companions themselves. This is extremely timely, given that there's this little telescope called the James Webb Space Telescope. You might have heard of it. Launched on Christmas. First images arrived 2 weeks ago. And just last week, the data started coming in from the early release science and other programs. And we're starting to get actual information from some directly imaged worlds. So I'm going to take you through what we know on these worlds. I'm going to take you through a little bit of 101 on directly imaged exoplanets and how Gaia is helping us understand them. And I want, as you listen to this talk, to consider this a challenge if you really understand what the word planet means when somebody says it to you. What is a planet? Pluto is not the only planet to be a problem for the definition of that word. By the end of this, you will see that the high mass end of things is also extremely problematic for the definition of the word planet. Let's start with a little 101 on the OG directly imaged exoplanets. And that is, the OG directly imaged planets, those are the ones that you can see in the sky. So Mercury, Venus, Mars, Jupiter, and Saturn. If anybody was outside sky watching in late June, you might have caught that there was a parade of planets happening, and you could actually catch each one of the visible planets in our solar system available to your eye, and the moon kind of did a little dance on them. This was a video that we rendered for the press for this from New York City. What do you want from a planet, right? What do you want? You want to see it. You want to physically see the light that's coming from it. You want to get that light, you want to break it up, and you want to see what kind of chemistry is driving these sources to look the way they do. We can do that for these planets. We can actually see them with our eyeballs. And it's the holy grail of exoplanet science. And the real holy grail of exoplanet science would be to get images like this. Everybody knows what planet that is, I hope. Not Mars, good guess. That one's red. This is Earth. We live here. This is our planet. This is a direct image of our planet. And what can you glean from this? We can see the clouds. We can see weather patterns. We can take images over and over and over again and calculate aspects of the world. You can get spectra. You can see biosignatures. We'd love to get to this holy grail. However, this is not the grail we're at yet. This is the grail we hope to achieve. We will all be dead by then, probably, hopefully. But otherwise, we want to achieve a moment where we can see planets. And we're doing that, but for very different kinds of worlds than, say, Earth-like planets. This is the real holy grail. Can I just see a show of hands in this room? How many people have seen this animation before? The majority of people, right? That's outstanding. I'm so excited to see that so many people have seen this, maybe used it in a public talk. This is what I like to call the Brad Pitt of exoplanetary systems. If you have a camera, you point it at it. It's so beautiful. There are 4 worlds going around this star, HR 8799. And Jason Wang has created this animation from images taken primarily from the Gemini Planet Imager. And you can see the planets going around the star. There are 4 in this particular case. And we can actually physically see them using an instrument that blocks the light of that very bright star. But we've also taken spectra of those sources, and I'll show you that in a second. Now, okay, a little bit more 101 information though. This is what we do for directly imaged exoplanets. What do we go after? Earth-like planets right now? Absolutely not. Not happening yet. We're going after big planets, big ones, Jupiter-like planets. They're big. They're young. Why are they young? They got to be hot. They got to be hot so that you can see them when you block the light from that parent star. Okay, now I am actually a brown dwarf scientist. So you guys are secretly going to have to also learn about brown dwarfs in this talk. And the reason is the following, to remind you what brown dwarfs are. When you think about mass space for compact objects, you've got stars, and we've learned a lot about stars, and Gaia tells us an enormous amount about stars. And then you've got planets, and I've got this little cartoon here, Sun on one side, Jupiter on the other. And then as you walk down in mass space from stars into Jupiter, you run into a class of objects that we classify as brown dwarfs. When you have a giant molecular cloud that's fragmenting off and creating compact sources, you reach a mass by which there's not enough mass in the fragment to get the core of the compact source hot enough to get nuclear burning going. So you don't get fusion going. Instead, get a little bit of heavy hydrogen burning. Deuterium can burn. But then the thing is like the compact object is just like an ember plucked from a fire, and it cools through its life. And as it does, it morphs between temperatures, between classes. And I'll zoom in on what those classes are. It morphs through these classes. The hottest of the brown dwarf classes are the L types. You can get up to about 3,000 degrees Kelvin or so. That's like the highest setting on a pottery kiln. You can think of that. The middle type class, now it's a middle type class, it used to be the coldest class, are the T type brown dwarfs. And then the coldest class are the Y type brown dwarfs. Brown dwarfs, brown dwarfs, brown dwarfs. Why do you have to remember this when I give you a directly imaged exoplanet talk? Because every single directly imaged exoplanet that is currently cataloged falls squarely in the temperature regime of a brown dwarf, falls squarely in the temperature regime of these objects, for which we have a multitude of beautiful data that can characterize and contextualize and really help you understand what that looks like. On top of which, Gaia has been a major aid in helping us understand brown dwarfs. They're kind of the bottom of the mass space that Gaia was able to give us astrometry on beyond our solar system. So the lowest mass objects that Gaia was able to access, very applicable to the directly imaged exoplanet world. Every single directly imaged exoplanet is in fact a secret brown dwarf. Makes you question what's a brown dwarf and what's a planet. Where do they cross? Where do you decide you found one versus the other? Typically, it's because you find a planet orbiting a star and you find a brown dwarf in isolation. I'm going to come back to that. Is that a good definition? I'll ask you guys at the end of that what you think. But a little bit more on the 101. So these classes of objects, you have to also think about them in terms of this degeneracy that exists between the mass, the age, and the temperature. This is a classic evolutionary diagram of brown dwarfs and planets and stars. On the x-axis here, you have the age of the source, 1 million years very young, 100 million years juvenile age, 10 billion years old. And then on the y-axis, I've given you the luminosity of the source, but as kind of like a helpful hint thing, I've also labeled on the far right side of this the kind of object that might have that luminosity from a spectral characteristic perspective, because directly imaged exoplanets, you acquire data that allows you to figure out what category or class of object that the compact source that you've discovered falls into. Now, just looking at this plot where each one of those lines is a prediction from models, from evolutionary models, of how the cooling sequence might flow for an object of a given mass. So each line is a given mass over time. And I've labeled them by anything above 75 times the mass of Jupiter, where you can definitely get nuclear burning, is a star. Green, between 75 down to 13 Jupiter masses, I've colored green and indicated it's a brown dwarf. Please don't quote me on that definition. That is not my happy definition. That just happens to be what's happening with deuterium burning in there. And then below 13 Jupiter masses, you don't get any heavy hydrogen. The thing just, you can see that line just cools right on off. But in looking at this, if you didn't know the age of your source, if you didn't know the age of the source, and you just figured out enough information from the spectra maybe to get the luminosity, to get the temperature class, you actually wouldn't really be sure what you were studying, because you wouldn't have access to the mass unless you could do a dynamical mass. And we'll get to that and how Gaia helps us with that in a second. But as you walk across a line of luminosity space, you see that that line from left to right here runs into each one of those color-coded categories. So you say, for instance, find yourself an L6 object, an object that looks like an L-class object. If you don't know the age, you don't know, is it very, very young? Maybe it's an upper SCO, orbiting an upper SCO type star. That would help you figure that out. It's a planet. It's below that 13 Jupiter mass. If it's juvenile age, maybe it's in the Pleiades or Hyades or something like that. There you go into the brown dwarf territory. Maybe it's a halo object sweeping in, older type object that's kind of sweeping in at maybe like 8 or 9 billion years old. It happens. Each one of those kinds of objects, the low mass star, the juvenile age brown dwarf, and the young planet, share the same effective temperature. So their direct imaging information, their spectral information, will mimic each other and look very similar. Frustrating, frankly, to everybody in here. Look at me right now. I am frustrated with that problem. It is very frustrating not to know the exact kind of object that you're studying. I would very much like to know what the mass is of my source that I'm studying. So Gaia is hot on the trail of helping us figure this kind of thing out. So you get your companions, directly imaged companions, and you're able to extract information about the host star that really allows you to extract age information about a companion, for instance. So let's go over what it is that Gaia tells us about directly imaged exoplanets in particular. Because by the way, you do also find brown dwarfs co-moving with a star. And you'll also see in a second that you also find them at the exact same age and in the same groups as you find the exoplanets, confusing the situation. But how does Gaia help us understand directly imaged exoplanets? Well, the two major things there that I popped right off of that evolutionary diagram that Gaia is helping us with is figuring out the luminosity of your source. It gives us a parallax for the host star, which automatically wins us an enormous amount of information, especially a very precise parallax. And it's helping us get into the age information. And I'm going to dig strong into that in the first section of the details of this talk. But it also gives us this other information. You learned yesterday in Tim's talk that you can get dynamical masses from the acceleration imprinted on the host star from the companion. You can get chemistry information, as we've all just learned with DR3 dropping a couple of weeks ago, an enormous amount of stellar information we've just acquired from the spectra that Gaia has given us. And then some really fun tidbits I'll tell you that Gaia also helps us understand about directly imaged exoplanets is their dynamical history. Wait for that one. That one's a real, that's a real doozy that you might not have seen coming. And then ultimately, Gaia is helping us dig deep into this question of formation of some of these sources. How did they form? All right, I'm going to go through these in step. And I'm going to start with age and what Gaia is helping us figure out about the ages of directly imaged exoplanets. So here's a little gallery of images of directly imaged worlds. They get their pictures, I used to call these selfies, but now I realize I'm not very good at this. They're Uzis or something because they're not taking it of themselves. We're taking it of them. So it's not actually a selfie of a planet. It's us taking a picture of them. All of these are images, hard-earned photons acquired for each one of these worlds that you can see in here. And labeled are the moving groups, the young moving groups that they belong to. TW Hydra, Beta Pictoris, Columba, AB Doratus, Tucana Horologium. Marina talked a lot about this 2 days ago. This is critical to directly imaged exoplanet work. You have to have the closest, youngest stars are the ideal candidates for direct imaging campaigns. I'll just repeat. The closest, youngest stars are the ideal candidates for direct imaging campaigns. You need to have a star that's young enough so that the planet is hot enough for you to be able to see it. You'd like it to be close by so that you're not fighting as hard to get to those photons. You would also like it to be close enough that you can have a better separation between that star and your world. All of this is critical. So who is going to give us a map of the best young stars near the sun? Well, that's Gaia. And here's my little aside on here, aside from the fact that I'll dig into that more deeply in a sec. But the other thing is I'm just going to spread these out and let you know that the other thing that Gaia has done is also given us isolated siblings of those exoplanets in those exact groups. So you can go to Beta Pictoris, you can go to TW Hydra, you can go to Columba, you can go to Tucana Horologium, and you can actually see isolated versions of the directly imaged exoplanets that are shown in these selfies, Uzis, whatever. You want HR8799b in isolation without the star? We've got it. You want Beta Pic B in isolation without the host star? We've got it. That kind of object, actually, Gaia has been able to directly look at. These are the isolated, often called brown dwarfs, but really sometimes referred to as free-floating planets, orphaned planets, or whatever. They don't have a host star, so if you're going to use companion as the definition of planet, clearly you've got a problem, you're not going to include them. But just so you all know, these sources help contextualize the directly imaged exoplanets. And I highlight Jonathan Gagne in here. I'll keep bringing him up. He's one of my closest collaborators, and we do a ton of work trying to dig out these young isolated objects, as well as trying to figure out these groups. So here's a little video rendering that I'll talk to as we go here. And what this is going to be a flight that we're going to take off from the solar neighborhood. We're kind of leaving Earth and the solar system. We're already out probably about 10, 15, 20 parsecs. And then we're going to keep flying out to about a kiloparsec. And as we fly out, all of these stars are mapped by their Gaia positions. Every one of these is a young star as mapped by Gaia. Gaia has discovered some of these as young stars that we previously did not know. And now as we keep moving out, we're going to get to about a kiloparsec away from the sun. And ladies and gentlemen, this is your young solar neighborhood. I love showing this. I love showing this in a dome. I love showing this in planetariums. I love playing with this data. Marina talked a lot about this in her talk. You see these strings. You see these clumps, these overdensities of stars. Some of them are really tightly bound, and you could walk outside, look up at the nighttime sky, and just pick them out. That's the Pleiades and the Hyades for you. Others of these are they are just too separate from each other to do that. And now I've turned time on at like 50,000 years per second and propagated forward the Gaia proper motions. And you can see how we're able to associate these stars with each other as they're co-moving. And you're watching these structures. This is not orbital integration, though that is something that we're working on in order to understand how these groups interact with each other, because that is also relevant to the directly imaged campaigns and worlds. All right, so Gaia has created the greatest map of the nearby young solar neighborhood that we have yet to have. It is, I can't give it enough praise, frankly. I can't give it enough praise from a star formation perspective, from an understanding a mass function perspective, from so many things. If I could give it A+++ forever, I would. But the thing that it provided for us for the direct imaging campaign is targets, and also homes for planets that we didn't know what their co-moving friends were prior to Gaia. So just to highlight some of the work that's been done on this, this is work by my team, by Jonathan Gagne and myself. The day any Gaia data drops, we immediately run to the data set and try and find the new young stars that had been previously missed. This is from Gagne and Faherty 2018 that came out right at DR2 day, April of 2018, where we just dug right in to find the nearby, the closest young stars that had been previously missed. And what were they going to be? This shows you the spectral type of sources versus the number of objects that were recovered. New candidate members of known groups maybe are in red, recovered known candidates are in that green, bona fide members are in blue. And what you see is a lot of the missed stars that are now new to our understanding are the later type colder objects, M-type objects, K stars. It's really hard to hide a young A star. Like they don't hide well in the solar neighborhood. They're just like beacons of X-ray flux and near UV. They do a lot of stuff that says young, 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 but you can hide M dwarfs, and those are great candidates to look for a directly imaged world. Another thing that I would point out that Gaia has provided for us is new groups to target for the planets. So that plot was of members of known associations that we've been studying for years, but then there is also these new groups that we now know. And attending this conference is Leslie Maranta. Leslie, maybe raise your hand and wave. Leslie, amazing, new grad student, University of Montreal, working with Jonathan and I. Have a look at a new paper that she dropped on arXiv right before DR3 came out. This is a new analysis of DR2 to find new associations previously missed. Are you going to find tight ones? Are you going to rediscover the Hyades and the Pleiades? You're going to find a new Hyades or Pleiades? No, you're not. That's not going to be hiding in the data set. What will be hiding is these more loosely bound, harder to figure out, wide across the sky because the sun is passing through them associations. And this is a figure from one of the plots in Leslie's paper that shows all of these new groups that are discovered. And if you look close in, you can see we're really targeting 100 parsecs from the sun, 150 parsecs from the sun. We have new groups, and more than that, we have new fluffy coronas and tidal tails that are associated with things like the Pleiades and with the Hyades that are very close by. All of this is very relevant to direct imaging campaigns. Once you have these sources ready for you, once you've got them, you can actually look for planets around them. And I just refer you to table 8 of Leslie's paper as well as evidence. We immediately went and looked at those stars that were newly assigned to a group to see if they had planets. And some of them did. None of them had a directly imaged planet. Some of them were just test objects of interest. Many of them actually were, or stars that people had targeted that just had previously not been associated with the group before. You can co-match this though with acceleration catalogs, find those closest stars, and then bam, you go from a fishing expedition, which has been the traditional way that directly imaged campaigns have proceeded, with having a good hint of where you might find a planet, to very direct, strong evidence for why you should go after a star. All right, on to the next topic that Gaia helps us with, and this is chemistry. And I'm going to take you through some data. I'm going to try and do this slowly. This could be a totally different colloquium or totally different talk. I'm going to take you through a couple of things with this and how we dissect this direct imaging information that we are obtaining from the companions. So, chemistry information. What does that mean? You heard Melissa Ness give a talk the other day on galactic cartography, archaeology. This is another movie that I've rendered for you. Starting close to Earth, so this is the view you'd have of stars. Clearly, that's the Kepler footprint that's there. All of the stars now, rather than being color-coded by their temperature, they're color-coded by their metallicity. They're color-coded by their iron abundance. Green is fairly solar-like. Blue is going to go off the gradient to where it's a lower metallicity. So this is actually color-coded right now by what Apogee and Gaia tell us, 2 high-resolution spectroscopic surveys. I just grabbed all of the data from that. I actually did this with Keith Hawkins, who's another galactic archaeologist, cartographer. And we're kind of flying around now, and you're seeing the distribution mapped by their Gaia positions of the stars, color-coded by their chemistry. And you might be noticing that it looks like there's kind of like these blue tips to the ends of the gradients of these stars as you move away. Now you can fly out and kind of see the disk of the Milky Way. And what you're actually looking at is the metallicity gradient from the disk, where the stars that you get older, you're moving farther away from the disk, and you're actually capturing some of the older information. This is actually a rendering that I made by flying on my computer, which is why you can see my mouse moving around. And I just wanted to show you guys also how these visualization tools help me contextualize some of the data I work with. All right, but chemistry. So why do you need to know this for exoplanets? This is an obligatory plot that one has to put up when you're talking about planets. And that is the following. You'd like to know how they formed. You'd like to know where in the disk they formed. And giant planets are hard. As I said at the start, how do you define when you've got a planet as your companion, maybe versus a brown dwarf that formed through the same kind of processes that the stars formed through the gravitational fragmentation of a giant molecular cloud that just broke off this big piece, versus accretion in a disk around a star. And this plot from Karen Oberg is showing you as you walk across a disk around a newly formed star, say, from the left-hand side of this plot to the right-hand side of the plot is showing you further away in the disk versus the carbon to oxygen ratio. The holy grail, the bad holy grail that we have of trying to decide if an object has formed within the disk or if it formed through a fragmentation process of sorts. And part of why we use this is because we can tell that the ratio of carbon to oxygen based on disk stars should really land at like something like 0.55. That's just the ratio of carbon to oxygen that we see across the disk of the Milky Way with looking at a lot of stars. But when you look at it across the solar nebula, you'll see there's points across a nebula around a star where you get a freeze out of different molecules. So you freeze out hot water somewhere around here. You're seeing it a couple of AU here. You're going to freeze out the water. And when that happens, you're going to suck some of the oxygen out of there. And so your C to O ratio is going to go up. So if you formed out here, your abundance in your atmosphere or your bulk abundance that you can extract from your directly imaged world is going to have a higher C to O. Same thing out here, carbon, this is where CO2 freezes out at like 10 AU. And so you're going to lose some carbon in there, but you're going to lose more oxygen. So your C to O ratio again goes up. Okay, so higher C to O ratio, maybe that's indicative of core accretion being your formation mechanism. And on top of that, what you need to know is you need to extract that carbon to oxygen ratio from your companion for your directly imaged world. Then you need to compare it to your host star. You need to know your host star really well. You need to get some abundance info. You need to get your metallicity info. And if you can get all that, then you can say something about the formation of your object. So let's look at some of the directly imaged data that exists. Again, zooming in on this selfie plot here of some worlds as characterized by the Gemini planet imager. And let's look at the data. So these are images, but we also have spectra now. You can go under the hood and see what the chemical composition is of these objects. On the x-axis here, you have wavelength, which is basically running across the near infrared from about 1 micron to about 2.5 microns. And on the y-axis, you've got flux that I've normalized in order to showcase for you what this beautiful library of objects looks like. But because I'm a brown dwarf scientist and I've already got analogs, I'll explain the chemistry to you using my library of objects. Some of these are observed, in fact, by Gaia, very similar to those directly imaged worlds. And in this, just to give you an idea of some of the chemistry that we're gleaning is look over here in K-band. You see this little drop here, this little divot in here. This is some CO that you're measuring right from your spectrum. You move over here into J-band and you have these beautiful absorption alkali lines. You've got this beautiful potassium in here. You get some sodium over here. You get these gorgeous shapes here, frustrating shapes too, of your J band into H band. You've got water vapor that's sculpting these spectra. This is sculpting brown dwarf spectra. This is sculpting directly imaged exoplanet data. What you can do with this information is once you've got your data, you can go and turn to theoretical models and say, okay, what do I expect to have in this object? Based on, you got to know the parameters of how old the source is. What's the log G? What's the metallicity? What's the carbon to oxygen ratio? What are the abundances in the host star? How will that help me understand and disentangle this directly imaged information? So you can go to the models, theoretical models that'll give you a grid of spectra to overlay on here to try and to match up what you're seeing. Or the more popular method right now in the era of the James Webb Space Telescope is to do this thing called the spectral inversion method or retrievals. And the retrievals method is a very popular way to start with the data. You start with your spectrum, and then you add in the chemistry, and you use physics that you know exists to churn out what is actually happening in the data. This could take a whole other colloquium, a whole other talk to go into, but it's not as relevant to this audience per se, but know that this retrievals method is the method of choice right now for extracting information in the era of the James Webb Space Telescope and all of this information, and that the tools that we have been developing and using on brown dwarfs are extremely relevant. What you back out of your retrieval is the ability to get a temperature pressure profile for your object and to parameterize clouds in your source, clouds and the chemistry in the clouds. That is hard. And so I'm going to show you, and this is the kind of output that you get from the retrieval method after you do churn it through your retrieval method. You get these annoying corner plots that tell you way too much information, but you can see towards the bottom here, you're getting this information that's very relevant to if you have a host star with chemistry information. You're getting metallicity, you're getting the C to O ratio, and then you're getting abundances of all of these great molecules. Know your host star, and you can know this stuff really, really well, okay? So I'll explain this to you with a beautiful little rendering so I can make this make sense why you want a Gaia type approach to being able to characterize the host star, because we have this great data from the secondary. Gaia gets us the parallax, beautiful parallax that we need in order to do that spectral inversion method really well. It really holds tight that spectral energy distribution, which is very sensitive to the process to try and fit the continuum of that spectrum, which is going to allow you to parameterize the clouds that are all over this thing. This is an artist's rendering of what these directly imaged exoplanets look like, also what brown dwarfs look like. They have enstatite clouds, phosphoryte clouds. They've got weather-related patterns that are running all over them. And what you want to know is you can't actually get to all of the cloud information. Best that we can through the near infrared and the mid infrared data is make some guesses at where within the depth of the atmosphere we're finding some of these enstatite and phosphorite clouds. But you want to know the chemistry of the host star really well in order to make sure you're not making some unbelievably bad statement about what could be driving the chemistry in the clouds of your object. You'd also like to be able to get to the C to O, and all C and O are also locked up, especially O, oxygen gets locked up in the clouds of these objects. So before anybody should make any presumptions about a carbon to oxygen ratio that they think can help them figure out what the formation mechanism is of their companion, make sure you understand what the clouds might be doing. How are you going to do that? Make sure you understand your host star. So all of it ties back to know thy star, know thy planet, hence know thy clouds. That's my new statement on that. All right. The last bit on this is luminosity, mass, and formation. Gaia gave us parallaxes for sources, which allows us to get to the luminosity. Recall from the beginning of the talk, I showed you the evolutionary diagram of, I remember, what did I have on there? Age. I had age on the x-axis, and I had luminosity on the y-axis. The majority of directly imaged exoplanets, definitely pre-Gaia, had model-dependent masses. Dynamical masses would be fantastic. You'll hear about some of that today. But we've been stuck with model-dependent masses. And the model-dependent masses really required us to really know the luminosity and the mass very well for directly imaged exoplanets. I have to say that before I start showing you these next plots, some of which you've seen before, because they're going to have mass on them. And that remains, as I said at the beginning, really annoying component of studying these objects. So this is a plot that you see over and over and over and over again in exoplanet talks. This is one that I pulled from a recent, very nice review paper that Thane Curry, Beth Biller, Anne-Marie Lagrange, others, 2022. It dropped this year. It's a great read on directly imaged exoplanets. I encourage you to download it and read it. This is showing you the semi-major axis of the companion of the binary versus the minimum mass in Earth masses, of course, because you have M sin I for the radial velocity planets. And so this is just the exoplanets from like the exoplanet archive. And you can see all of the different ways that they've been discovered here with direct imaging on the upper far right corner of this plot. They are the most distant from their host stars, as one would expect if you're going to try and access their information. And they are the most massive of these. But all the information that you might want is not actually wrapped up in this plot yet, because it's zoomed in on just the planets. Masses, again, for the directly imaged exoplanets that are on here, for the most part, these are plotted on here, not as a dynamical mass, but as a model-dependent mass that was acquired once you knew what the luminosity and the age of the source was, and you were able to back it out of the information that you had using models. But I'm going to zoom out to a plot that I prefer to show that's more inclusive of placing these objects in context with stars and with brown dwarfs. And as I've zoomed out here, what you can see on the x-axis is the separation of the system in astronomical units and the mass ratio. So it's the same x-axis, but the y-axis, I've chosen to change it for you to not be about the secondary, but rather about the ratio of the primary to the secondary, which is one potential method for deciding if you are looking at a companion that formed through the accretion process versus the companion that formed via the gravitational fragmentation process. And in looking at this plot, you see a couple of interesting things that are going on. I've tried to lay out for you solar system type objects that will help contextualize what kinds of separations you're looking at for these systems. And by the way, this is chock full of observational biases. Just because you don't find things in the top up in here, does it mean that they don't exist in nature? No, that's not what it means. This is just the collection of objects that have currently been observed. We're capturing within this plot a lot of observational biases. The pink blobs at the top, this is largely Gaia discoveries of star-star binaries. And to take you through two, so bottom left-hand corner here, separation real tight, companion to host. Mass ratio of host to companion, super tiny. So you got a real small object compared to the host star. So I think everybody would be probably very comfortable calling this corner planetary objects, exoplanets. And then on this other corner, it's near equal mass. So they're 1 to 1. And they're really far away from each other, beyond the Oort cloud, outside of what maybe you would even call the solar neighborhoods, the solar system of our own. Okay, so these, maybe you have no problem calling them stellar binaries. But what about that intermediary area, the transition? What the heck's going on there? And guess who lands there? The majority of directly imaged exoplanets. That's frustrating. No, that's frustrating. Can Gaia help us discern what might be going on there? Maybe we're trying to figure this out in a holistic way. I'd love to get masses for every one of these so that instead of having all these model dependent masses, we'd be able to lay this plot out in mass space. But let's just zoom in on a couple of the objects so that I can explain what some of these mean. Okay, first of all, HR 8799. Oh, let me just go back for a sec. HR 8799 systems, they are in this transition space where I would call these the stellar binaries formed through the gravitational fragmentation method. These are the exoplanet companions, probably formed through accretion. And these, something happened. And HR 8799 systems have always been a problematic because they're kind of detached from the exoplanets. They're close, but they're detached from the stellar binaries, but they're closer to the exoplanets. All right, let's look at HR 8799E in here. What is the mass of that? You're going to hear about this from Mirek later today, I think. Because the nice thing that Gaia gives us on that host star is that it's an accelerating host star at 5 sigma. And you're able to back out of it the mass of the companion, specifically attributed to the E planet, which is the innermost planet in this system, HR 8799E. We do have spectral information on it as a late type L dwarf. It is very comparable to a number of objects that I've studied my entire career. Its age is a little bit problematic and questionable. Gaia is helping us. HR 8799 is thought to be in the Columba moving group, maybe also beta pic. Who knows if that. Gaia is going to help us figure this out, and it will ultimately come down to really understanding the young solar neighborhood. But mass is really nailed down for the companion in this one, helping us to understand exactly where it should be on that plot. So is it it's at the hairy edge of where we're comfortable saying that this could have formed through the accretion process. Let's talk about another object, a particularly favorite of mine at this time, and that's too fast. That's this object, BD plus 60, 1417b, and I've highlighted it for you as a 5-point star in this. And this, you can see now, it's kind of like hanging out by the stars, but it's got a really small mass ratio and it's really widely separated. So what the heck's going on there? Well, this is a discovery that was made by my team. And I think it's a cool story because this star is a very nearby young star. It's about 40 parsecs away. It was known to be young for 50 years or for many years. Lithium, X-ray, solar analog, great target, was looked at by a bunch of exoplanet direct imaging campaigns, really close into the host, and nothing was found. And so they gave up on it because, you only have so much observing time. I co-founded this citizen science project called Backyard Worlds, where we're basically searching the whole sky for previously missed brown dwarfs. And one of the citizens brought this one to my attention. As you can see, the star, the young star at the center here, is bouncing back and forth as these are epochs of Ys taken over time. And you can see the star bouncing back and forth. And this thing was there. You see that object there bouncing back and forth? It actually was in all the reject catalogs of 2MASS and Ys because it's too close to the host star. So it's close. It's not close enough to be found by direct imaging campaigns, but it's too close to the host star to have come out in catalog searches because it gets lost in the diffraction spike. But if you blink images and play with the contrast of the images, you can find it. It's brought to my attention. I went to the telescope. I took a spectrum of it like I do of other objects. And I was just like, boom, whoa. How did I just see HR 8799 again? And that's what it looked like spectrally. And that's what it looked like when I used the parallax of the host star and figured out what its luminosity was. So this is a direct analog, but it's very widely separated from the host star. It's 37 arc seconds separated, or 1600 AU separated from the host. The age of the thing is 50 to 150 million years. Gaia was very helpful in helping me try and give it the best age I could. It has metallicity information, log G, all of these things that are in Gaia that I'm now using because DR3 just came out to try and figure out what's happening with this system. But very useful in understanding this borderline case of a companion. It is in the exoplanet archive. It is a very close by, excellent target for campaigns. And by the way, this is part of why I wanted to show this to you. The other thing that Gaia gives us for this and for the collection of directly imaged worlds is the V broad value, V sin I. If you combine that with the rotational information, which you can get from tests now, which is what we did for this one, you're able to get the inclination angle of the system. And when you get a fully resolved system like the one that we've got here, BD plus 60, 14, 17, you can do the same trick on the companion. We have HST monitoring of the companion there, BD plus 60. We're going to get its weather-related phenomenon, its rotation rate. We already got its V sin I through Keck. And we're going to be able to compare and contrast the inclination angles of these systems. Thank you, Gaia, for giving us the V broad of the primary. And that'll give us another lever on potential formation mechanism for the source. Okay, two other sources to give you on this plot. Another major directly imaged object is this one called Ross 458c on this plot. It's in this unfortunate area, again, kind of close to the stellar binaries. So we scratch our heads like, how did it form? What is it? What are we going to do with it? But part of why it's so exciting is because it's a major JWST target. Data is coming in very soon on this source. We're going to have a full spectrum of it from the near infrared to the mid infrared. We're going to perform that retrievals analysis on it. We're going to back out those abundances. We need to understand the host star, which is itself a binary. Gaia gives us the parallax of the system. We get the elbow for the companion really nicely from this. It has given us kinematics that are indicative of it being a younger source. The RUI is highly indicative of the host star being a spectroscopic binary, which it is. It has a RUI of 4. It is a JWST target. It's getting MIRI data as we speak to get the spectrum for this source. We're going to measure the C to O ratio of it. We need to know the host star really well. It's an M dwarf binary, so that's why the mass ratio is where it is on that previous plot that I just showed you, 1100 AU. But excitingly, I'll just say it because sometimes I just talk too much about interesting science that we're doing. I think we may have found through Gaia the home association of Ross 458c. So that's another thing, like great target. Everybody loved it. JWST definitely in the first light kind of thing. People wanted to go after this. But we didn't know exactly who its friends were and how old it actually was because we weren't sure about it. But Gaia gives us the kinematic associations that are allowing us to place it with other stars that it's co-moving with. Okay. And then the last one in this particular list is one of my favorites for this kind of description and what Gaia has brought us. Another JWST GTO target is HD 106906b. And you can see I've highlighted its position on this mass separation diagram here. It's in the highway. It's in this annoying area. Kind of separated from the spectral binaries. It's not close enough to the planets. Scratch your head, core accretion, gravitational fragmentation. How did it form? Widely separated. But here's the cool thing that people did with this system. HD 106906b was discovered in a Magellan imaging campaign. Vanessa Bailey published a paper on it in 2014. Very widely separated, 7.1 arc seconds, nicely resolved, easy to just spot. Plucked it right out there. You can see it. It's this source right here, as opposed to these background stars. You know, they get so enticing, but they're just in the background there. And this is a wide field from the Hubble Space Telescope. And then zoomed in here, there's the host star that's masked out. It was looked at by the Gemini Planet Imager. And when they looked at this, so, you know, we got a spectrum of this. We've got great spectral information on it. It's a mid-type L dwarf. It's got crazy clouds. All the retrieval stuff is going to happen on this source when the JWST data comes in. But there's a lot of head scratching on this object because it is a spectroscopic binary, the primary here. And when they took the Gemini Planet Imager, you saw this like asymmetric structure to the debris disk, plus the planet, which is 11 Jupiter masses because this host star is in the SCO-SEN association at just a couple million years old. So you can get the model induced mass here. That's where that comes from. But it's like really widely separated and it had this asymmetric disk. So it was like, what's going on there? What happened? Kind of looks like something happened dynamically. Well, Robert DeRosa, along with Paul Kalitz, did this cool trick that I keep wanting to play with all of the exoplanets, which is they did a traceback of the group in order to look for a stellar flyby, which may have induced the shape of the disk. And actually, Ruth Murray Clay had looked at this image from this debris disk image and thought, you know, that kind of structure, what might cause such a thing is a flyby. But how on earth are you going to be able to access that information? Well, Gaia helps you because it has such pristine kinematics. You know that you have a co-moving, co-evolving young association with the SCO-SEN association. And so they did trace it back. And what did they find? They found 2 candidate stars. They're both named in this paper if you're interested, that were likely flybys that were coplanar with the disk. It was modeled, and it looks like they could very well be the culprit for placing the planet where it is and the disk in the shape that it was. Awesome, in my opinion, because there's a lot of mysteries about planetary architecture that I think might be helped if you had a little bit of extra info, because stellar flybys totally happen. Just check out the archive as 3 different papers dropped after the DR3 data release came out because you looked at the radial velocities and noticed that you had this whole system of objects. I've just got one more slide and then we're done for questions, right? Yes. Okay. Last thing on this is future-based direct imaging that Gaia helps us with. There is this system called 14 Hercules BC. It is one of the closest giant exoplanet systems to the sun. In working with a group on the 20 parsec sample, myself and a postdoc working with me, Daniela Bardelez-Gaglufi, noticed that this had an awesome radial velocity trend and also an acceleration. So you might notice this. This is a plot from Orvara. This was work done very, very much collaboratively with Tim Brandt and Yi Ting and his team at UC Santa Barbara to try and disentangle what this system might be. And I'll just play the video and finish explaining this. 14 HER is a radial velocity detected multi-planet system. A B and a C are there, accelerating the star and showing a radial velocity. In looking and decoupling what might be happening with the masses of these, we were able to back out the masses using the acceleration and the radial velocity information and discover, as we fly towards the host star, that the white lines is the orbit of the 2 white lines are the orbits of the 2 planets in the system. And they do look like they're also off kilter from each other, not coplanar, possibly also induced by some sort of planetary car crash. Maybe they ejected a planet along the way. Maybe a stellar flyby happened. But 2 big planets, just a couple of Jupiter masses, 5 to 9 Jupiter masses or so, basically cold brown dwarfs. They are the direct imaging sources of the future, possibly JWST, but definitely the Roman telescope. So just so you know, checking out these accelerations do set you up for next generation. All right, I'll leave my conclusions here. Gaia is an aid in direct imaging work of exoplanets. We get all of this great information on the host stars, and it's setting us up for the next generation of imaging. And I'll stop there and take any questions.
Okay. Thanks very much, Jackie. Are there any questions? We have 6-7 minutes to go. Yes. Anybody?
We have 2 online questions. I'm just going to ask those while waiting for opinions. So the first question online said, are Uranus and Neptune insufficiently OG?
Uranus and Neptune. What was the question about them?
I think it's because when you showed the first couple slides, you showed like, you know, all the OG planets. And this is just a question saying why the other 2 are not there.
Okay, because yeah, so the OG directly imaged planets, Uranus and Neptune are below the detection threshold of your eye. So I was trying to give you the original directly imaged worlds, which were ones that people before the telescope could have found. And that's why I didn't include Uranus and Neptune. They are, of course, planets. I wasn't trying to say they aren't. It's just that you can't see them with your eye.
Yeah. So the second question from the Slack channel says, on what basis are the groups formed?
At what basis are the groups formed? That is one of my favorite questions to try and address scientifically. We don't know, you have to work with modelers in order to decide if the groups and the dissipation of the groups, the densities of the groups that you're seeing matches what might happen based on some initial conditions. Because essentially we're catching them at different times. And you have very young groups that are very dense. You have very young groups that are not very dense. You have older groups that are kind of dense, and you have older groups that aren't. And so they clearly have different pathways to arriving at their current construction. And the beautiful thing about Gaia is that it is just giving us the observed area of the galaxy that we're in. So you look around and you're seeing the different stages and pulling it all together. I just submitted a proposal on this. So if anybody's listening, it's going to review it, please give me time and money. We're going to use these time frame stamps from Gaia in order to really say, like, well, we know this is what it definitely looks like in our area, from the highest mass objects to the lowest mass objects. So we'll be able to do really detailed construction.
Is it on? Okay. I was wondering about, for like substellar and low mass members of groups, how precise the astrometry is for those. Like, are there issues with the Gaia having trouble seeing the very faint objects and then getting precise kinematics to identify them as group members?
Yeah, that's a great question. Like, how good is Gaia at measuring the astrometry for some of these sources? They tend to be the basement of what Gaia can do. Like, they tend to come in at like G of 20 or so. We really push the boundary. And, but even that is precise enough for us, the uncertainties on them is very small because they're very close by. So you're talking about like the closest one in particular, I could tell you about 2MASS 0355, one of my favorites. That source is at 11 parsecs. So that's part of why Gaia is able to do it. And that one comes in at like 20 Jupiter masses. It's in AB Doradus. It's actually on, it's in one of, should be on this plot somewhere. But the idea there is that you can get a very small percentage on the luminosity with Gaia, better than what I was doing from the ground, for sure.
So is there much, like, I guess, smaller chances of like chance alignments in the kinematic space then?
Chance alignments of the kinematics of these young objects. I mean, the nice thing is that you never want to rely on kinematics alone as your indication that you found a young source. What you really want to know is that you've got an object that is got other indications of youth. So we supplement it with other factors of the object. We get the spectra, we see that it's got a lot of low gravity features. And so the story holds together across a lot of parameters. Gaia is just like the chef's kiss and also the anchor, I would say, for knowing that these things are for sure in these groups.
Great talk, thank you. I mean, you described the delineation between stars and planets as being very frustrating, and I agree. So I'm wondering if you could give us your thoughts at where that line is.
Yeah, so if you have to force me to give you a definition, I'm so annoyed at life because nature hasn't given us anything that we can really lean into. So I actually prefer not to use the word planet as much as I can. I choose to use the word world. You might have noticed I kept switching that nomenclature as I was talking, because ultimately I would really like some formation signature as my go-to. So ultimately these directly imaged worlds, which have all this chemistry information that I can directly compare to the host star, is what I'm going to lean into alongside a mass measurement and a separation so that I can play on that mass ratio figure. But ultimately, there's no smoking gun yet to tell you, did it form through accretion or did it form through the gravitational fragmentation process, or maybe even some intermediary fragmentation process where you fragment out of the disk somewhere. So I'm just going to punt and say, I don't have a definition for higher mass planets. I just call them worlds.
Cool, thank you.
I encourage you all to call them worlds.
Hi, I was wondering if you could go a bit more into how you use the Gaia data to help confirm these stellar flybys. Is it just the inclination? of these stars with respect to the host and position data that you're looking at?
Yeah, so this is excellent work done by astronomers. Corin Baylor-Jones has done a huge amount on this, and I encourage you to check out some of his papers. I have an undergraduate that's working on this as well, appending the Gaia sample with brown dwarfs. All you need is full kinematics. You need X, Y, Z, U, V, W velocities. And you can use a linear approximation for stellar flybys to move the linear trajectory forward and backwards and just measure the perihelion distance and time. It's quite a simple approach if you don't have to integrate too far back or too far forward in order to incorporate the galactic potential, which is when things get messy. But a true stellar flyby of a 20 parsec sample object means that you end up being able to do, just give me the best kinematics from Gaia and you win.
Okay, thank you.
Lucy, just a comment, just to reiterate something Jackie said. We're not necessarily shifting paradigm, but we're bumping a paradigm here. World is the right word to use. Been using that in planetary class for a decade or so, because that's, Titan's a world. It's not really just a moon. And a piece of information about formation versus what these objects are. If you take the most common type of star in the universe, which is an M dwarf, 75% of all stars, and you look at the companions to the M dwarfs, you're going to find about 30 of them have a stellar companion. You're going to find about 2 of them have a Jupiter, and you're going to find about 2 of them have a brown dwarf companion, if that. So I would contend, because brown dwarfs we always think are from fragmentation and not so much from a disk, that stars form like stars, planets form like planets, and brown dwarfs form like brown dwarfs.
Yeah, what the last comment on that too is the one thing that we are trying is to look at the initial mass function of the solar neighborhood, look at the initial mass function of all these groups Gaia has. And what you might be seeing hints at is an overdensity at a certain mass at this transition area where possibly you can get objects created through both mechanisms, through planetary type things in a disk, and also through a gravitational fragmentation of the collapse. It's very exciting work. I encourage you to check out Davy Kirkpatrick's work that's about to come out on this, as well as other things that say my team are doing, and just keep questioning what you classify things as. I'll stop there so we can keep to time. Okay.
Thank you very much, everyone.